Hello everyone, I'm Dr. Alok Atwal and I welcome you all on my last lecture on fluid mechanics having course code ME404. So in last video we have seen two numericals related to Newton's law of viscosity. Now we will see two more numerical on the same topic. So this is the seventh lecture of the series with viscosity numerical part 2. So let us start with the next numerical. See what is given in the problem. In a 50 mm long journal bearing arrangement, there is a clearance between the two at concentric condition is 0.1 mm. The diameter of shaft is given 20 mm and it rotates at 3000 rpm. The dynamic viscosity of the lubricant between the journal bearing arrangement is 0.01 Pascal second. Okay, and Pascal, we know that Pascal is Newton per meter square, so it is given in SI unit, that is Newton second per meter square. And the velocity variation in the lubricant is linear. So we have to take tau is equal to mu du by dy as our base formula. Considering the lubricant to be Newtonian, calculate the frictional torque the journal has to overcome and the corresponding power loss. So first we have to calculate the frictional torque, and once we calculate the frictional torque, we can calculate the power loss. Okay, so let us see the arrangement, what type of arrangement it is. This is the condition in which there is a shaft of diameter 20 mm. Okay, and the length of it is given 50 mm. This is our bearing. Okay, and it is rotating in a sleeve of diameter which is 0.2 mm more than diameter of the bearing, because there is a clearance of 0.1 meter. So 0.1 meter plus 0.1 meter, it is 0.2 mm. So not meter, it is mm. Okay, and the length of the bearing is given 50 mm. So from here we can get that the clearance which is dy is 0.1 mm, and the oil which is used in between these two arrangements is having viscosity of 0.01 Newton second per meter square. Okay, and with this arrangement we have to calculate the torque. So let us write the given condition. Length is 50 mm. We have to convert it in meter, that is 50 into 10 to the power minus 3 meter. Clearance, it is given 0.1 mm. So we have to calculate it in meter. 0.1 into 10 to the power minus 3 meter. Diameter of shaft is 20 into 10 to the power minus 3 meter. Speed is given 3000 rpm, and dynamic viscosity is given 0.01 Pascal second, that is Newton second per meter square. Okay, now from Newton's law of viscosity we have tau is equal to mu du by dy, which can be written as u by t. Okay, t is thickness, means clearance. Okay, now if shear stresses can be written like this, shear force can be written as F, shear force F is equal to mu into u by t into area. Now which area? This is in the form of cylinder, so we have to take curved surface area of cylinder, that is 2 into pi into r into L. So this will be our area. So shear force or viscous resistance of force can be calculated as shear stress into area. Shear stress we have mu into u by t into area 2 pi r L. Now torque, if the force is known, torque can be calculated as viscous force into torque r, that is equal to r, because the shear stress is taking place on the surface of this bearing. So we have to calculate arm length as half of this diameter, that is radius. Now substituting the value, but before substituting the value we have to calculate u, because u is not given here. So u can be calculated as pi dn by 60, because rpm is given. So linear velocity can be calculated by pi into d into n by 60, where d is given 20 mm, we have converted it in meter, and n is given 3000 rpm. So we get u, that is linear velocity, as 3.14 meter per second. Okay, now substituting the values in this equation, we get torque is equal to 0.1 mu is given. We have substituted the value of u, we have substituted the value of dy, 2 pi into r into L. So, and this is again r. So we get torque as 9.85 into 10 to the power minus 3 Newton meter. So now we have to calculate the power loss. So power loss is calculated by torque as P is equal to torque into omega. So to calculate the power loss, first we have to calculate the angular velocity of this shaft. So angular velocity is given by 2 pi n by 60. N is given. We have substituted the value here and we get omega as 314 radian per second. Now the power utilized to overcome the frictional resistance is given by P is equal to T into tau, that is P we have just calculated, omega, that is angular velocity we have calculated, we have substituted here, we get power loss as 3.09 watt. This is very important problem and have been asked in university exam as well. Now let us move to the next problem. This is again very conceptual and very important problem. So here it is given there is a flat plate of 0.3 meter square area moves edgewise through a oil between large fixed parallel planes 10 centimeter apart. Okay, so there is a two parallel planes and in between that there is a oil, and in that oil a flat plate having area 0.3 meter square is moving. Okay, and the velocity of plate is given 0.6 meter per second and the oil is given 0. Having kinematic viscosity 0.45 into 10 to the power minus 4 meter square per second. So here kinematic viscosity is given. This is 10 to the power minus 4. Okay. So to apply it in Newton's law of viscosity, first we have to convert this kinematic viscosity into dynamic viscosity, and for converting that we need the density of that oil. So for density, specific gravity is given 0.8. So from this we can calculate density of oil, and with the help of density of oil we can calculate the dynamic viscosity of the oil. Now in this problem we have to calculate the drag force in two different conditions. First condition is when the moving plate is exactly in between the fixed parallel planes, and second condition if that moving plate is at a distance of 2.5 centimeter from any one of the plane. So there are two different conditions and we will see that as the position of that place is changing, the shear stress also changes. Okay, so first shear stress and drag force will change. So first condition is that the plate is exactly in between the two parallel planes. So its distance from both the fixed parallel plane is same, that is 5 centimeter, because the distance between these two parallel planes is 10 centimeter. And we have taken the thickness of this plate as negligible. Okay. So given that area of the plate, which area? The area which is we are not able to see in this figure. Okay. This is the side view. And if we see it from the top, we will able to see this area 0.3 meter square. Distance between the plate is 10 centimeter. Velocity of thin plate is 0.6 meter per second. Kinematic viscosity is given. Specific gravity is given. So first, what we have to do, we have to let us consider that there are two forces acting. Obviously, this plate above this plate, oil is there. Below this plate, oil is there. So there will be a two forces acting in this plate. Okay. Now suppose F1 is the force acting on the upper side of the plate and F2 is acting on the lower side of the plate. So total force can be calculated by the addition of these two forces F1 and F2. So total force F will be F1 plus F2. Now dynamic viscosity, there is a relation between kinematic viscosity and dynamic viscosity. From that relation, we can calculate dynamic viscosity. So density is specific gravity into 1000 into if we multiply this density with kinematic viscosity, we will get dynamic viscosity. Substituting the values, we get dynamic viscosity as 0.036 Newton second per meter square. Okay. Now let us consider that shear stress tau1 acting on the upper side of the plate is given by mu du by dy. So dy is the distance between the fixed parallel plane and the upper surface of the plate. So that distance is 5 centimeter. We have to convert it in meters. So we will get 0.05 meter. And when we substitute all the values here, we get tau is equal to 0.432 Newton per meter square. Okay. Now shear force. If shear stress is this, shear force will be shear stress into area, and area is given 0.3 meter. So substituting this, we will get F1 as 0.1296 Newton. And this plate is traveling at a center, so F1 is obviously equal to F2, but here we are calculating first tau2. Tau2 is again, we'll get same because the distance is same, the viscosity is same, the area of the plate is same, everything is same, so we'll get similar result of F1 and F2. And once we add both F1 and F2, we get total force that is 0.2592 Newton. So this is very simple case. Okay. Now in second case, what it is saying that the plate is not at the center of the parallel plane, it is at a distance of 2.5 centimeter of one plate. So obviously it will be at a distance of 7.5 centimeter from the second plate. So let us move to the second condition. This is like this, that from the upper plate we have considered that the plate is moving in such a way that its distance from the upper plate is 2.5 centimeter and its distance from the lower plate is 7.5 centimeter. Okay. So similar calculation we have to do. We have to calculate the shear stress 1, that is nu, which is remains same. Du will remain same, but dy will change this time. In earlier case, dy is 0.05 meter. In both the cases, here the dy for first case will be 0.075 meter. So from this we will get shear stress as 0.288 Newton per meter square and shear force multiplied by 0.3, that is 0.0864 Newton. And in second case, the shear stress tau 2 will be calculated by same formula, but here dy changes to 0.025. Okay, so we will get shear stress different from the shear stress that have been calculated here. Okay, so here we get shear stress as 0.864 and shear force likewise will be changed to 0.2592 Newton. The total force will be 0.3456 Newton. So we have seen that by changing the position of the plate, the total drag force is changing. Okay, so this is the important numerical that we have discussed here in this video. Thank you.